Hello everybody and welcome to the overview of the production workflow for the Pan-European Climate Database version 4.2. In this presentation we will go through an overview of the C3S Energy Lot 2 contract, the production workflow for the PECD version 4.2, the spatial and temporal interpolation procedures, and the wind profile power law. The main objective of the C3S Energy Lot 2 is to support ENTSO-E in the preparation of the Pan-European Climate Database, also known as the PECD. To achieve this, the contract focuses on key climate variables including 2-meter temperature, wind speed at 10 meters and 100 meters, total precipitation, and surface solar radiation downwards. These climate variables are then converted into energy-relevant indicators, which include wind power, both onshore and offshore, solar photovoltaic power, concentrated solar power, and hydropower generation and inflow. The historical climate data stream extends from 1950 to the present, while the projection stream goes from 2015 up to 2100. This slide illustrates the workflow for producing PECD version 4.2, showing the processing steps for both historical and projection streams. For the historical stream, we start with ERA 5 reanalysis data, where preprocessing includes calculating wind speed from U and V components, fixing known ERA 5 issues, and converting GHI units. Next, we apply bias adjustment to wind speed at 10 meters and 100 meters. For the projection stream, we begin with CMIP6 models, where the preprocessing includes spatial and temporal interpolation, since the CMIP6 models do not have the same resolution as the ERA 5 reanalysis, and then also in this case computing wind speed from U and V components. Bias adjustment is then applied to all the variables using different methods. From this, wind speed at 100 meters is derived using the wind profile power law. At this point, the gridded climate indicators are ready. Then the workflow proceeds with the computation of the population-weighted temperature. To obtain the aggregated climate indicators, a spatial aggregation procedure is performed, which allows to compute average values at country and sub-country level. To compute the energy indicators, some installed capacity and generation data are needed to train and validate the conversion models. There are 4 main energy conversion models: wind power, solar photovoltaic power, concentrated solar power, and hydropower. Exclusion layers are then applied if needed, and spatial aggregation is performed again to produce aggregated energy indicators at country and sub-country level. We are going now to expand a little more on the spatial and temporal interpolation procedures and on the wind profile power law that are used in the projection stream. The CMIP6 models have a coarse spatial resolution of about 100 kilometers and a temporal resolution of 3 hours. To make the data compatible with ERA 5 and suitable for our applications, we perform both spatial and temporal interpolation. For spatial interpolation, we use bilinear interpolation to regrid the data to a final resolution of 0.25 degree, as shown in the example on the left. For temporal interpolation, we refine the data to 1 hour, and this is done using several different methods. We use spline interpolation for variables like temperature and wind speed, and the interpolation of the clearness index for solar radiation. The graph on the right illustrates temporal interpolation for 2-meter temperature. The original 3-hourly data is shown in red and the interpolated hourly data in blue. We will further explore the different temporal interpolation techniques in the next slide. For temporal interpolation of temperature and wind components, we use the spline. This method processes data in 3-day windows, keeping only the day in the middle, and iterates through each day. Secondly, for GHI, a different approach is used due to its strong diurnal cycle. Instead of directly interpolating irradiance, we interpolate the clearness index, which reflects atmospheric transmissivity. This index is then converted back to irradiance, preserving the daily profile. However, this method assumes stable weather conditions within the original time steps. Finally, for total precipitation, no temporal interpolation is applied because it is aggregated daily. On the right, you can see an example of temporal interpolation for GHI, where the original data points are marked in blue and the interpolated curve is shown in red. Wind speed measurements are usually taken at a standard height of 10 meters above ground level. This is done to minimize the influence of obstacles such as buildings, terrain, and vegetation, ensuring the data is as accurate as possible for open ground conditions. However, for energy modeling purposes, we often need wind speed data at 100 meters above ground level, as this corresponds to the typical height of modern wind turbines. To estimate wind speed at this height, we use the wind profile power law, shown here. The formula relates wind speeds at two heights, v1 and v2, using an empirically derived coefficient alpha and the ratio of the two heights, h1 and h2. The value of alpha depends on atmospheric stability, and under neutral conditions it is approximately 0.143. This method allows us to scale wind speed data from 10 meters to the required height of 100 meters, ensuring its relevance for energy applications. The alpha coefficient determines how wind speed changes with height, and it's not fixed. In fact, it depends on the local conditions of the area. And in this case, we calculate alpha using data from ERA5 wind speed at 10 and 100 meters. This allows us to account for variations in surface roughness and other local features. Temporal variations in alpha are also considered by stratifying the coefficient by the month and the hour of the day. This ensures that we can capture changes in atmospheric stability throughout the day and across the seasons. As shown in the graph on the left, the mean value of alpha varies significantly depending on the time of the day and the month. On the right, the box and the whisker plot shows the distribution of alpha values for each hour across the entire PECD domain. The interquartile range highlights the typical variability, while the whiskers capture extreme values. This calculation of alpha allows us to derive wind speeds at 100 meters, even when direct measurements are not available, such as in CMIP6 projections. This makes it an essential tool for climate and energy applications. Thank you for the attention, and do not hesitate to reach out if you have any questions.